All right. Let's do some web apps. All right, let's get started. So we had the expected deadline for homework 2 this morning. Hopefully a lot of y'all are doing good with this. If not, you probably understand this warning at this point if you did give it a try for the expected and didn't make it. If you did make it, awesome. Feeling good. But yeah, homework 2 is done. I'm done with homework 2 content. If there are any quick questions about homework 2, if there's any lingering issues with it, now's the time. Let me know. Otherwise, the course is moving on to homework 3. All right, moving on. So homework 3 is posted. By the way, these do collapse if you want to collapse them. For homework 3, we want to take our server and make it live. That's our whole goal with homework 3. We're going to do that with WebSockets. So we're going to have live chat between users where you can post something and immediately see what that person has posted in all other browsers for all other clients. So today we're going to go through what's called the WebSocket Handshake. So after today, you can already do Learning Objective 1 on the homework. After Wednesday, you'll be able to do Learning Objectives 2. So you're going to be ready for both learning objectives pretty quickly. Honestly, application objective 1 as well. You'll be able to do after Wednesday's lecture. So we're going to get through a lot of the content of this homework pretty quick. This homework is, I don't want to say the first, but this homework is very implementation heavy, I guess is the word. Like, it doesn't take me a ton of time in lecture to talk about the protocol of WebSockets, the idea behind them, how they work. There's not a ton to it, but when you go to code it, I'm sure in a few weeks you'll agree with me, it is difficult to code and get everything just right and working just right. So the homework content we'll get through pretty quick in lecture, but it may take quite a while to code. I think, in my opinion, I think homework 3 difficulty is about in line with homework 2 difficulty. So if you're trying to allocate your time and budget your time accordingly, I'd say it's about the same, especially for the learning objectives. Application objective 3 on both homeworks 2 and 3 are pretty challenging, I'll say. But the learning objectives are about on par. Actually, yeah, across the board, homework 2 and homework 3 are about on par, in my opinion. I always have to say in my opinion, because somebody's going to come to me and be like, yo, those were way off. For one particular student, one of you, yeah, they'll probably feel way off. But I think overall, across the whole course, they'll be about in line. All right, no questions before we get into things? Difficulty? Oh, hey, I actually answered that question. I didn't even see that in chat. Difficulty from 2 to 3. Yeah, about even. The difficulty curve of this course is homework 1 is by far the easiest one. Homework 2, there's a big jump up. Homework 3, I think it levels off a bit, about the same. And then for homework 4, it's a little bit of a dip. So homework 4, I think, is easier than homeworks 2 or 3. So there won't be, like, once you're done with homework 2, there shouldn't be, I'll put an asterisk. In my opinion, there's not. There's not another difficulty spike after homework 2. From 1 to 2, it's a big spike. If you can survive homework 2, you're going to survive the course. You're going to be fine for the rest of the course. It'll still take that amount of work, it'll be work and everything, but you have what it takes. You have the determination and the drive and everything it takes to complete the whole course if you can get through homework 2. Bless you. That's usually how I build the difficulty curves in my course. I don't believe in a strictly increasing difficulty curve. Some courses just spike way up at the end. Some courses are more linear and just constantly increase, constantly get more and more intense as the semester goes. I don't like building curves like that. I like them to quickly get to the difficulty of the course and then level off and then taper off a little at the end. At the end of each semester, that's when every course is absolutely crushing you. So in my courses, I like to take a step back at that time and not just keep pounding you with stuff. That said, you also have the project at the end of the semester. A lot of groups wait till, I know it's shocking, but wait till the last 2 weeks or even 1 week of the semester to do the whole project. So the course won't back off if you're one of those teams, but the design of the course is designed to back off at the end. No other questions? Any other questions? Anything? WebSockets. WebSockets are such a fun topic. Let's talk about it. So WebSockets, the problem we're solving here is that AJAX is kind of a pain. So we saw AJAX. AJAX was a way to send requests to the server after the page loads, and we could make our sites more dynamic. We can have more interaction with the server after the first page load. Before AJAX, we can send the HTML. The HTML has links in it. The browser will send requests for each one of those extra resources that we have, our CSS, our JavaScript, any multimedia. Get all those responses, mash it all together, and render the web page, and then that's it. There's no more communication between the client and the server unless the page reloads, and we go through that whole process again of requesting the HTML, getting the new content and everything. We'd have to do that to be able to do that. Now, sometimes those page reloads, like for homework 2, are caused by a form submission. So we can still get some dynamic features in our websites, but it's not great. So we threw AJAX at it to be able to make requests that don't require reload, so we can have more dynamic content, content that's changing after the page loads. And to make it feel live, we used polling. If you're doing application objective 3 on homework 2, you're using polling to, at regular intervals, request new content and say, hey, you got new content for me? Hey, you got new content for me? And we use polling at every 1 second in lecture in the example, and 2 seconds in my extension that we saw last time. And then we can expand that to long polling, which actually does solve the problem pretty much as well as WebSockets, but a little trickier to set up. But it does solve the problem. It solves the problem pretty well. Long polling, you send a request just like polling, but instead of the server responding to the request right away and saying, no, I don't have any more information for you. No, I don't have any more information for you. With long polling, the server would get the request and just sit on it and just not do anything with it unless there was information to send to the client. So whenever there was information to send, it would respond to the long polling request immediately, and then the client would send another long poll request. The long polls can time out. After 15 seconds or so, we'll just respond with no new data and then get a new request immediately. But there would always be an open HTTP request sitting at the server, so whenever the server had something to say to the client, it would respond to that open request and then get a new open request. Which again works well, but do you really want to do that on homework? Maybe someday I'll make a class do that. Maybe for an application objective 3, I'll have them do that. But I don't want to put you through that. So our answer is going to be WebSockets. WebSockets is a full duplex communication. You create a connection between server and client, and both server and client can send messages to each other whenever they want. Full two-way communication. This is what we want. This is going to give us all the functionality we could ever ask for, that we could ever dream of. Full two-way communication. And these will be effectively real-time. There will always be network delays, but it'll be as real-time as we can possibly get. We can't really get more efficient than WebSockets. I think I can say that confidently. We can't get any more efficient than WebSockets without sacrificing reliability. If we want to just send raw IP packets and just hope they get there, we get a little bit faster. But WebSockets is about the best we can do. So the beauty of WebSockets, what a WebSocket actually is just a TCP connection. That's it. It's a TCP connection. So what we're going to see with WebSockets, which we've used TCP all semester. So what we're going to see with WebSockets is when you make an HTTP request, that's sent over a TCP socket connection. So instead of doing something really fancy, special, brand new thing called WebSockets over here that we do, instead, what we're going to do is create the TCP connection, send an HTTP request over it, and that request is going to say, hey, server, let's just use this TCP connection that we already have. We already established the TCP connection to send this HTTP request, and you're going to send me a response, and we're just going to throw this TCP connection out. Or, by the way, I don't really talk about it in class, but there's that keep alive header you probably saw a lot. You can use that and then reuse the same TCP connection for multiple HTTP requests. In this course, we just throw away the TCP connection and create a new one each time we send a message. So what this HTTP request says, hey, instead of throwing this TCP connection away, just getting rid of it, disconnecting, let's just keep this thing open. We'll label it as a WebSocket TCP connection, and then we'll just communicate over that TCP connection till one of us closes the connection. And that's, in a nutshell, that's what WebSockets are. It's just saying, hey, let's just use this TCP connection. Instead of for HTTP, we'll just communicate over using the WebSocket protocol instead of the HTTP protocol. And then after that connection is switched to a WebSocket connection, then any bytes that you read, you should interpret as WebSocket bytes. Frames, that we'll start calling them on Wednesday, we'll treat them as WebSocket frames instead of HTTP requests. So fundamentally, the concept behind a WebSocket is really simple. It's just saying, hey, let's use that TCP connection for two-way communication, because TCP already does that. TCP is two-way communication. It's HTTP that's restricting us. HTTP says, no, it's a request-response protocol. You don't respond to anything unless you get a request. That's HTTP saying that. But it's built on TCP, which is already full two-way communication. WebSockets just says, let's just use that TCP socket. Why are we doing anything else? So it's kind of beautiful in its elegance, is that it's mostly taking protocols away and getting to a simpler time of just using TCP. So to establish a WebSocket connection, we have to go through what's called the WebSocket Handshake, which is going to guarantee, I'm hesitant to use the word guarantee, but it's going to give client and server confidence that they're both speaking the same protocol. We saw this way back, literally lecture 1, it got pushed to lecture 2. Lecture 2, with the TCP connection, when we want to establish a TCP connection, we go through that three-way handshake. And the purpose of that handshake was to have confidence that each side speaks TCP and speaks it properly, is able to decode the messages that it sent and receives, decode the messages it receives, and then send messages in the proper format. Same thing with WebSockets. We want that same guarantee. We're going to get I'm using guarantee again. We want that same level of confidence. We're going to do it in a bit of a different way, but we still want the same thing. We want to know that when I send this request for WebSocket connection, I want to know that that server actually speaks WebSocket WebSockets, before I keep this TCP connection open with a server that is misconfigured, that isn't actually doing the thing it's supposed to do. So that's what we want. We want a handshake, and then after the handshake, we're going to leave that TCP connection open, and then we're going to be able to send messages back and forth. If the server wants to send a client a message, you just send it over the WebSocket. You don't have to do any long pulling bullcrap, keeping hanging on requests or anything. You just say, well, we got this TCP connection open. Here's your message. Just fling over a message over the WebSocket. So to do this handshake, the client is going to send a very specific HTTP request that's going to have these 3 headers. It's going to be a GET request to whatever path you choose, whatever path you set up your server for, or whatever path I happen to write in the homework doc. I forgot what it is. I think it's /socket. And it's going to have these three headers: connection, upgrade, upgrade WebSocket. Notice this is not a typo. WebSocket has a lowercase w, upgrade has a capital U. I don't know why, but that's just the way it is. Those headers with those values. And the header names will always be uppercase letters in HTTP 1.1. Why am I hesitating on that one? If you do look in your browser, by the way, if you do go visit other sites and you notice that their headers don't always start with capital letters, check the HTTP protocol number. It's probably HTTP 2.0 or some quick, or I forget what the other ones are called off the top of my head, but some protocol other than HTTP 1.1. So that's the only reason you'll see different things sometimes. For our HTTP 1.1 servers, uppercase letters here. And then the sec WebSocket key, which is going to have some random value that you have to read. I don't know if I mentioned it even all that many times this semester, but if you haven't written your general header parsing code yet, you should have written it in homework 1 if you followed my recommendation. But here's another case where you have to read the value of a header. You had in homework 2, you had to read the boundary. Here you have to read the WebSocket key. In homework 4, you'll have to read all of the cookie headers. You'll get a lot of mileage out of that code. If you haven't yet, if you haven't written code that iterates through all of the headers of a GET request, of an HTTP request, and throw them all in a key value store of some kind, if you haven't written that code, what are you waiting for? Write that code. It's going to save you all kinds of time. I see students all the time, each time they need to read a header, they'll write custom code to read that individual header, and I see that code usually because they have to come to office hours because the code's broken. If you just write the general method one time, make sure it works once, and then just use it throughout the whole semester, you'll have a lot less broken code each time. And then you're going to respond with a request. You're going to respond with a response. You're going to respond with a response with these headers: the connection upgrade, the upgrade WebSocket. These just have to be identical to the ones that you got. You can hard code those. Nothing wrong with hard coding those. In fact, you can assume that you're going to get these headers. I won't be mad if you don't read these ones at all. If you get a GET request for your WebSocket path and you just assume that it's an upgrade request, it's perfectly fine. You're going to respond with these two headers hard-coded, and then sec WebSocket accept with some accept response. So most of this is pretty straightforward. We've done headers and HTTP requests and responses so far. The big thing with the handshake, and the handshake is all of Learning Objective 1, the big thing with the handshake is that random key and the accept response. What are those values going to be? Now, the random key you're going to read, it's literally a random value, or at least random to us. There might be some determinism of how to generate it. But random to us value, and we have to take that value and generate a very specific value for the accept response and send that back to the client. That's what's going to get our guarantee. That's what's going to give us our confidence, give the client confidence that we are speaking the protocol the right way. When we send this accept response and it's actually the right value, the right very specific value, then the client's going to say, okay, you speak WebSockets, Mr. Server. Like, well, we got this. We can talk over WebSockets. This is great. If you don't send that right value, even if it's 1 bit off, just going to be errors. So how do we actually generate that? This is, I would say, the most important slide in today's lecture. This is the one that you'll reference as you're doing the homework. This is the one that I'll pull up or ask you to pull up in office hours if you have a question about it. This is Objective 1 in one slide. So when you get that key, you're going to read the key header, get the value, and extract that. You're going to append this value without the quotes. I saw somebody put the quotes in there. Y'all are computer scientists. You should know the quotes don't go in there. This value, without the quotes, to the end of the key that you read. This is a very specific, very exact value, a very exact string, a globally unique ID for the WebSocket protocol. If you look at the RFC for WebSockets, the actual definition of the WebSocket protocol, this string is in there, and it says this exact string, this is the one that you append. So it has to be exactly that. You're going to compute the SHA-1 hash of that. Bless you. And then you're going to base 64 encode the hash. And that's your value for the accept. And this one, I forgot to mention caching so far. And this is going to ensure client's going to be like, yeah, you speak WebSockets. This is such a very specific thing to do. You're not going to generate the correct accept value on accident. Nobody's going to do that. With very, very high probability, if you get the right accept, it's because the server actually did implement WebSockets properly. You're not going to get this exact value, the SHA-1 hash, and base 64. Like, there's enough entropy there that you're not going to get the right value if you're not following this procedure. And also to avoid caching, there's a few things in WebSockets you're going to see specifically each message that's sent. We're going to do some cache breaking stuff. We're going to bust up some cache. We might have some aggressive intermediary code that wants to cache things. So we're going to have our code. We're not building any caching in our servers. You're not required to anyway. But we might have some code in between our server and the internet that we're running. We're going to see in homework 4, we're going to use Nginx as a reverse proxy. And Nginx likes to cache things. It's going to cache the hell out of things if it can. So Nginx might cache things if it sees, okay, we're getting a request for get/socket. And it looks identical to a request that I got before. And last time the server sent back this exact response. Well, I'm not even going to talk to the server. I'm just going to respond with that response that the server sent last time. It's a GET request. Like, there shouldn't be an issue with that. They're just requesting some content. I'm going to give them that content. So it's tempting for whoever's developing Nginx to add that functionality. Or you might have any other number of layers. Like for your homework, you might have Flask in the middle there between your code and Nginx, and then Nginx talking to any one of those layers might be caching, even if you don't explicitly implement caching. So if every time you get a request, there's a different random key and you're sending a different random accept, well, random from their perspective, it'll just look like random garbage. But it makes the request and response always different. So we're going to avoid caching because they're going to say, well, this is a different request. The headers aren't the same. I can't send the same response. Because if it gets cached and it's just whatever, here's what the server sent last time, the client's going to say, okay, I'm going to keep this TCP connection open and treat it as a WebSocket connection, and I'm going to send and receive WebSocket frames over this connection. And the server says nothing because it never got the request. That's a problem. So avoiding caching is quite important when it comes to WebSockets. Anything WebSockets shouldn't be cached. And once we establish that connection, we keep the TCP connection open. Why did my phone go to sleep? It hasn't been that long. Inheritance? Wait, no. Where are we? We're not talking about inheritance here. Will the quiz this week include comparators? That's not right. That was at least 23 minutes after their lecture. Is the random key generated? Stone Narwhal, I think, is asking the question that needs my attention. Is the random key generated by the browser or by our front end? By the browser. Why would it cache if there is a different key? Get request is different. It won't. So that's the reason for the key, is to break caching. That's one reason for the key is to break caching. So with the key, nothing gets cached. Problem solved. Where does the globally unique ID come from? From the actual spec. From the RFC for WebSockets. It's actually part of the protocol design. In that spec, it says, here's this big long string. You have to use this if you're using WebSockets. Yep.
How fast can the client server communicate? Are limited, or is it just based
How fast it can what? I missed part of it. It's as fast as it can go, I guess. There's nothing in WebSockets that limits that. And WebSockets is designed to be as fast as it can. It's really optimal in what it does. So it's going to be the regular TCP overhead, which honestly isn't much. Most of that overhead is during the handshake, and that's already done. Once that's established, we just have a connection where we're sending almost raw IP packets over the internet, which is as fast as we can get. If the messages we're sending are pretty large, it'll get split into multiple IP packets, and TCP will do its thing with sequence numbers and all that stuff. So a little bit of overhead there. WebSockets themselves have almost no overhead. So it's as fast as we can go. Then, of course, network delays. If you have a WebSocket connection with someone in California, you're going to have a few tenths of a second delay, which is still baffles me. That's still wild that that's the case. How fast we could send messages anywhere on the planet. You only notice it if you're like playing a game where 0.2 of a second of lag is important. So when we do establish, there was one question there I gave a half an answer to. By the browser. Oh yeah, because we're going to talk about the front end stuff. It's by the browser. In the front end, we're going to call a function which is going to do it for us. The browser will do it when it gets that function call. All right, so once we have this connection, two-way communication via WebSocket Frames. Frames we're going to talk about in depth on Wednesday. I just want to give a quick, brief intro to Frames today. But a frame is going to be a specific structure of our messages. And yes, we're going to parse at the bit level. Get ready for bits. This is where things get really fun. So this is a progression. I mentioned the progression a few times, just kind of the way the course happened. This wasn't planned or anything, but I like the way it ended up. Homework 1, you do string parsing. Homework 2, you do byte parsing. Homework 3, you do bit parsing. So we're going all the way to the bit level. Maybe I'm one of the only ones, but I get excited over this stuff because in classes like 191 and 241, 341, 220 these days, you talk a lot about bits, and you hear all the time, computers only speak ones and zeros. It's all bits. But you never actually use that information. At least I haven't outside of WebSockets, and a few niche applications that I had. You don't really use that fact that everything's bits. But in WebSockets, you actually get to that level where you actually have to care that the bytes that you're reading are 8 individual bits, and you're going to read those bits sometimes one at a time, and extract information from them. And this is one reason why WebSockets are so efficient. It doesn't waste a single bit. Bits aren't even wasted. Not even wasting bytes. We're not even wasting bits. Here's what a WebSocket frame looks like. This is what we're going to spend Wednesday talking about. We're going to piece apart everything that's here, but just a very quick overview. We've seen this format when I showed IP and TCP, but we don't have to actually get our hands on those protocols in this course. We just have the library do it for us. Socket Server just takes care of all that for us in our operating system. With WebSockets, we actually have to care about this format, so let's talk about it a little bit. This is a visual representation of the bits, where this is 4 bytes wide, so 32 bits, and when we read our bytes off of the WebSocket, we get 8 bits at a time. So if you were to read one single byte from your TCP stream, and it's a WebSocket connection, it's been upgraded to WebSockets, you did the handshake and all that, and somebody sends you a message, you read 1 byte, you're going to get these first 8 bits. And then out of that byte, the first bit is your fin bit, you have 3 reserve bits, and you have a 4-bit opcode. So you have 3 pieces of information in just the first byte of information that's sent. You have another byte. When you read the next byte, you're going to get this mask bit and then a 7-bit payload. Payload length. A 4-byte masking key, and then your actual payload, which is masked. Unless you're sending larger messages, there's 1, 2, 3, 4, 5, 6 bytes of overhead. This is why WebSockets are so efficient. It's such an elegant, clean protocol. 6 bytes of overhead each time you send a WebSocket message. That's not much. 6 bytes of overhead. Think of your HTTP requests and responses. Just to say HTTP/1.1, you've already have more overhead than a WebSocket frame, and you haven't even started communicating anything significant. By the time you get to the end of the headers, how many bytes are not necessarily wasted, but how many bytes of overhead you have in every HTTP request and response is absolutely massive compared to the overhead in a WebSocket frame of 6 bytes. So these are defined to be efficient. It's about as close as we can get to just using raw TCP connections, but having just a little bit of overhead to organize the data, organize the bytes that we're sending over those TCP connections. We will mask. We have this 4-byte masking key. Again, more details on Wednesday, but just briefly. This masking key is going to mask the payload data. Instead of actually sending the payload, which is the actual message, whatever the user or server is sending over the internet, over this connection, this is going to be masked, which means each 4 bytes of payload data are XORed with the masking key. And then when you receive a message, you're going to XOR again with the masking key, which is going to cancel out the masking key and give you back the original data. And again, this is to prevent caching. So the mask is different every single time a frame is sent. That means every time data is sent, a frame is sent over a WebSocket connection, it's going to look different. Even if you say the same thing, if you're in a chat and you're just spamming the same thing over and over and over again, every time you send a web frame, it's going to look different because it's going to have a different masking key. And again, we're going to avoid caching that way. That the messages are always going to look different, even if it's the same thing. So, any questions so far? I should give it a little bit of a rest. I'll put this slide up and ask while I wait for questions. Bit setting for peripheral control enable also happens in. Oh yeah, if you're taking hardware classes, yeah, that's definitely an exception. I mean, if you're just software engineering, you don't really see bit stuff. Yeah, if you're taking hardware classes, you're going to be concerned about bits a lot more than I was in my career, in my education. Yeah, any hardware class, you better be concerned about bits. But this is one strictly software application where you have to be concerned about bits. Yeah, computer engineering for the win on the bit stuff. Maybe I should have done computer engineering, like when we get to the bit level. Not all the time, but it just makes it more clear. Like when you're at the bit level, let me say it the other way. Like if you're coding in Python, you're so far removed from what's actually happening in the computer. Everything's basically magic at that point. By the time you get to the bit level, even in Python, I guess, even if you're using Python at the bit level, once you get to the bit level, like the whole veil is pulled away, and it's like, yeah, you're just manipulating ones and zeros. That's what you're doing. That's what we do as programmers. When you do bit parsing with WebSocket Frames, it's very apparent that that's what you're doing. There's no magical thing sitting between you and those ones and zeros. It's just you and the ones and zeros. I think it's fun. Very eye-opening of what we do as developers. All right. So let's talk about the front end. The front end code's given to you. There's a big JavaScript file in Homework 3. It's too big to just paste in the homework document, so there's a link to it. That's why you didn't see it when I briefly scrolled through things. There's a little bit of HTML that I paste in there, but the JavaScript file, it's a separate thing. But part of that is the WebSocket setup. We're going to have these lines of code. Of course, for your applications or even for your homework, you can change this around and have it do other stuff as long as you still fulfill the objectives. But this is how we're going to use WebSockets in the front end. So the first line here, we're going to create a, I don't know why I didn't use const there, but we're going to create a WebSocket connection. We're going to call this constructor. This is what's going to actually do the handshake stuff on the client side. This is what's going to generate that random key and fire off the HTTP request. We just do this, and we get that HTTP request for the WebSocket handshake. So we create a new WebSocket connection, and we're going to specify the URL for that connection. We're going to use the WebSocket protocol, ws:// instead of HTTP. We're going to use the host name. I'm going to use window.location.host. Please use this. For homework 3, you're expected to cut and paste my JavaScript file, so you don't really have to make a choice. You'd have to intentionally break this. On your other projects, whenever you're doing this in other places, even if it's not WebSockets, but whenever you need the host name, please use window.location.host. This is going to take the host of whatever sent you this code. So you make a request, the browser makes a request to your server, gets the HTML, makes another request for the JavaScript, gets this JavaScript. The host is going to be whatever the server name is that it requested the HTML and the JavaScript from. So we get the code, and host is going to be that host name. This is important because if you hard code this, what people will do, and what I've had people do, my brother did this on a project, and it caused a bug, and then I had to go and fix it because he put the wrong thing here. What people will do, and what my brother did, was put localhost right here, or localhost :8080 for our homework. And that'll work on your laptop, and that'll work in your development environment. But then you're ready to deploy, you're ready to launch your app to the world, and you buy mycoolapp.com, and you go host your site at mycoolapp.com. Your host name is now mycoolapp.com. It's not localhost anymore, so this front-end code will break because it's trying to connect to your client's localhost. Somebody visits your web page, and then it makes a request, tries to open a WebSocket connection to their laptop and not your server, which obviously doesn't work. And everything breaks. If you use window.location.host, I run this locally for testing. That's localhost. I go to deploy, and my users run this same exact code. That's going to be mycoolapp.com. You're just going to get the host dynamically, and then you never have to think about it. You never have to do, which I blame my brother, but I did this to myself before too. Do a find and replace on the whole project, look for localhost, and then just go through and replace them all with window.location.host. So I'd recommend using this for your homework. This is going to have the same effect as having localhost :8080 right there, because that's what window.location.host is going to be for that. And then socket, this is whatever path you choose. I have it as either socket or WebSocket, I forget, in the JavaScript that I give you. Whatever the homework doc says, that'll be the right one. I don't remember off the top of my head. But this is whatever path you have, whatever path your server is listening to for WebSocket connections. As long as this matches that path, you're going to be good. And then whenever you want to handle a message, you have the socket.onMessage. This is going to react to message events by calling this function, whatever function you give it. I'm giving it this render messages function, and this will be called with the message that the server sent to you. In your front-end code, you don't have to worry about the fin bits and payload length. The browser's going to do all that for you, and it's just going to give you the message that was sent, just the message. And then do whatever you want. I'm just logging it to the screen. And then finally, send message. If you want to send a message to the server, socket.send. That's it, baby. I'm giving it a string here. It's going to send this string. It's going to do the payload length. It's going to do the masking. It's going to do all of that stuff for me and send this a frame with this payload to the server. So the browser really does most of the heavy lifting for us here. We just have to call the right functions. I guess technically methods, but so Wednesday, it's this right here. That's what we want to mess with on Wednesday. Any Questions? What do the 0, 1, 2, 3 on the top of the diagram represent? Where's my slide with it? That's the bit number. So this is bit 0, 1, 2, 3, 4, 5, 6, so on, 9, and then bit 10, 11. So the 1 kind of goes with these. 11, 12, 3, 13, 14, 20, 21, 30, 31. So 0 through 31 for our 32 bits for our 8 bytes. But that's the bit number. Jesse did a triple major, Lamau. Using bits is fun until a single mistake and an already hard to remember address breaks everything. Yeah, bits. There is a downside to bits. You'll all feel it through homework 3. It's fun, but yeah, it can be frustrating. If you're literally 1 bit off anywhere, everything blows up. So be very careful when writing that code. I'd say this is one of the assignments. I think homework 2 also is, but when you get to this bit parsing, it's one of them things where if you're the type of student who, when you approach a homework, you just kind of bash random things and hope it's right, run your server and just hope that everything works, you're going to have a bad time on this one. You really got to think through what you're doing. I'll recommend unit tests. Actually, that's the next thing I'm going to do is recommend unit testing. When you're doing your WebSocket stuff, it's one of the times where unit testing does save you tons of time. I know nobody likes testing, but this is one case where I don't really see another way that's going to be efficient than unit testing. Let's talk about testing a little bit. I don't know if I'll really be able to get both of these on the screen at the same time. The font's going to be too small. But let's look at the WebSocket Handshake. And we want to make sure that we're doing this the right way. I do, like I just prefaced, I do recommend that you set up test cases. But how are we going to do that? How are we going to set up our test cases? So let me hope that I have nothing sensitive in this. Okay, that's good. That was my lecture example where we requested my server code and successfully attacked my server by requesting an arbitrary file. So I didn't leak anything there, like last time. And what I want to do is get a test case and then go through the procedure just to make sure that I understand what the handshake is supposed to do, what I'm supposed to compute. And we'll try to do this in the last few minutes. I think we'll get there. So first, I'm going to go to a website that I know uses WebSockets. So I know Twitch uses WebSockets for its web chat. Let's try to find a non-offensive stream, hopefully. And I'm going to go to the site. I'm going to go to Inspect Element, open up our developer tools, go to Network, refresh the page just to be sure. And I'm going to get all kinds of requests. Oh, I forgot to mention did I not mention that? The response code. I didn't mention it. Hopefully it was in my slide somewhere. But when you respond to the WebSocket Handshake, when you get the upgrade request, you're going to respond with a 101 switching protocols message. So we respond with the 101, which makes it really convenient here. I want to get to my WebSocket connections. I'm going to sort by status code and find the 101s because Twitch has all kinds of stuff going on here. So I'm going to go to one of these. I'm going to go to the chat one. And I can go to this messages tab. This helps for debugging. This shows me all the WebSocket messages that are sent and received. This is everybody who's chatting in chat, of course, in this application. But I can go to headers, more importantly for this conversation, and I can get this header right here, the accept. I did it a little backwards. I'm going to paste it over here. And on the request headers, I'm going to see my WebSocket key. So the server was sent this key and it responded with that accept. There's a test case right there. I have a valid input-output behavior that my compute accept should be able to compute. If I give my compute accept method, if I'm writing a compute accept method and I give it this, I better see exactly this. So let's try not in code right now, but let's try to compute. Let's try to get from this to this, doing it a bit manually. So with this, we have two algorithms we need. We need SHA-1. SHA-1 is an algorithm, whether you're using a library in your programming language or a tool online like this. Doesn't matter. It is an algorithm. It has to be implemented the same every single time, no matter who's implementing it. It is an actual algorithm. So I'm going to take this value here, going to paste it. I'm going to go to my slide, and the way it selects on the slide is always wonky, but let's do this. Let's erase the quotes and compute the SHA-1 hash. So that's our first step. We're going to concatenate this value, compute the SHA-1 hash, and now if we base 64 encode it, we should already be home. So let's base 64 encode this thing. And if I can get the right value here, and base 64 calculator. And when I paste this and decode, no, I want to encode. Let me go to a different one. That one had way too much going on. I want to, yeah, there we go. I want a box where I can paste. And when I compute this, we'll get the wrong value. Just calling that so you know I didn't do it wrong. I'm going to get the wrong value here. So I appended, I SHA-1, got the SHA-1 hash, I base 64 encoded it, and I got the wrong value here. This is something that you have to be watchful for when you're base 64 encoding. This is a hex string. These are or not even a hex string. This is a hex value. You can see it's all the letters are A through F or numbers. This is a hex value. And when I got this calculator, or if you just base 64 encode, import, and do it, it might be treating it as a string. So this is treating it as, it says right here, text. So this is treating it as ASCII text or UTF-8 text, and then converting those to bytes. It's giving me the wrong thing. It's not what I want. So when I compute the base 64 encoding, I want to make sure I'm using a hex encoder. Because I want to go from my hex value. Just give me one that looks clean. I just want a box and a button. Is that so much to ask? Base 64 to hex, hex to base 64, hex to base 64, paste, convert. No, I pasted the wrong one. Oh, that might blow off my timing. No, just, why isn't this simpler? Be simpler. Base 64 to hex. I want to go the other way around. Oh my goodness. Base 64 decoder. I want a base 64 encoder. I'm going back to the first one. Base 64 to hex. No, go. On the left. Encoders. Hex to base 6. Thank you. And this should be the right value. And it should be identical. You want to make sure it's bit for bit identical. It should be the exact identical string